Okay, good evening. Before we start, maybe we can review what we discussed last time. Then discuss the problem I give you on the matching. Then, and also reminder for homework, number 1 due date is next week.
Hello, Professor.
Yeah.
I think someone is there in the waiting room. Could you please allow?
Yeah, I entered. I do not know why, just curious why they need the waiting room. I thought all students should be able to come
I
in,
think
right?
you have enabled the waiting room. For that reason, they're getting the option.
Oh. But anyway, I think
Thank you.
now everyone is in. Okay. So let's start. Quick review what we discussed. See. Okay. So basically, we start with a real chapter. So in a particular method we call greedy algorithm, and we look at 3 examples. Still someone entered. So let's first discuss what's the main idea of a greedy. So the greedy is try to maximize overall utility of some process by making immediate optimal choice at each sub-stage. So assuming that you solve a problem, you use multiple stage, right? So you try to look at each sub-stage one at a time and make an optimal choice. So this picture shows like people are greedy, right? The more money you get, the better. But does that mean that you will be happy, very happy at the end? It's not necessary. But in some cases, especially the problem we discuss in this chapter, you will get the optimal result. And we look at 3 algorithms. The first one we call interval scheduling. And pay attention to the method we use. In interval scheduling, we use a concept so-called stay ahead. Stay ahead means that you try to always stay ahead or compare with other method. And this is also one way to prove the optimality. Right? So we use the concept of finishing time, earliest finishing time. So that means this will give you more room, more time to select the remaining jobs. That's why it's optimal. And the other problem we call the interval partitioning. So that means you have lots of overlap jobs. You want to finish all of them. What you try to do, you recruit the minimum number of workers. Or like you have many classes in our department, we try to use a minimum number of room to accommodate all the classes. So what you need to do is to find a simple structure, basically a low bound. So if you can state the low bound, that means it's guaranteed optimal. The last one is scheduling the minimum lateness. So you have a lots of job, you have to finish all of them. But in addition, there is a deadline. So what you try to do is to find the best schedule so that the maximum delay or maximum lateness of each job will be minimized. So this is a totally new, different way to prove the optimality through an iterative exchange. So they call exchange argument. So we will go through each one by one. So this is the first one we already probably know. You have lots of overlap schedule. So what's the best way to do? You can use the starting time first, right? Earliest starting time. We already proved this is not the best one. Or you want to pick a task with a minimum duration so that you don't occupy too much slot. It turned out this is not good either. So this is kind of important. See, the first one is earliest time, so it's not good because earliest time you may have a very long job. So remember the goal of this problem is to maximize total number of jobs. You don't care about the duration. And if you want to pick a one with a minimum interval, and the second case shows that this is not good because you can pick a 2 instead of 1. And another one is that you want to pick the minimum with minimum conflicts, fewest number of conflicts. Conflicts means that if you have overlap. See in the middle one, the gray color one, or dark one, so it has only 2 conflicts. And all the other one has a 4 conflict or 3 conflicts. No, actually 1 conflict or 2 conflicts. Yeah, all the other one is 3 conflicts. But turn out this is not a good choice because if you select this one, you can pick a 2 more. The best solution actually to be the first row. Right? So all this is not optimal. So then the optimal solution is that you use the minimum earliest finishing time. So this gives you more room to schedule the remaining job. Right? So the proof, I'm not going to go through this one. In the book, I give you an interesting proof by contradiction. Right? So you have a 2 sequence and you find the first one that differ, but then you introduce some kind of contradiction. So I'm not going to go through that. But the idea is quite simple because you have only the total number of hours, fixed number of the day. So when you do schedule, if you can finish the first job as soon as possible, always is the best. So that's the solution. Then we discussed that there are many extensions, like a weighted interval schedule problem. For example, each job has some kind of weight. Then you cannot use greedy anymore. And we introduced later in 3 weeks dynamic programming approach to solve that problem. So you have to pay really attention to the type of problem, read carefully, and what's the objective. Then for interval partition, so it's right. So this is just the amount of jobs. So you need to recruit the minimum number of workers to finish all jobs, assuming that each worker can only do 1 job at a time. So you can see that this is one schedule. You have to recruit 4 jobs, four persons, but that's not optimal. The optimal is 3. Right? Now the questions when you design the algorithm, right? So how you know that the algorithm is the best one? So we already look at the previous case, so-called look ahead argument. This one is using the low bound argument. What means low bound argument? So the idea of a low bound is this one. So if you have a vertical cut, like a cut means that you just pick a time and then you see that how many jobs are running concurrently at the same time. So in this case, it's 3. So you know that each person can only work on 1 job at a time. So this definitely 3 is a low bound. You have to recruit 3, right? So that's give an idea. So if you can come up with some greedy algorithm that match the low bound, then that's the best one. So the algorithm turned out to be quite simple also. What you try to do, you look at the earliest starting time. So you look at the earliest starting time. You schedule 1 by 1, right? So based on the starting time, then you look at 1 by 1. So the minute whenever the time comes when the job has to start, then you see that if there are any in this classroom available, or like a workers available. If available, you just schedule. If it's not available, that means all workers are busy. What means all workers are busy? Suppose you already pick a K, right? K workers. So all workers busy, and then you have to introduce 1 more. So it's K plus 1. So this match to the low bound we just discussed, right? So I mean, at this particular time, everyone's busy, so you don't have other choice. So you have to introduce another one. So that's the idea. So you just keep on adding the more and more, and until obviously if there is available one, So we call available means compatible. That means there's no conflict. Then you just schedule to the 1, like an empty classroom. Otherwise, you have to introduce 1. So then the low bound argument works. Right? So I'm not going to go through this detail. Then the last one is kind of interesting, is scheduling the minimized lateness. So the concept of lateness is important. Again, you can use the example of a schedule. So all of us are very busy. Remember the first problem is like interval schedule. You have lots of work to do, but you only select a subset. You want to select the maximum subset. But this problem is slightly different in the sense that now you have to finish all of them, and each has a deadline. So what you try to do is to minimize the damage. What means damage? Means delay or lateness. So lateness is defined as the finishing time minus the deadline. If you meet the deadline, the lateness is 0. For example, if someone asks you to finish the job at 6, you finish at 8, then lateness is 2, right? So you see that? So some job has a lateness, some has no lateness, means 0. So the requirement is important to schedule all jobs to minimize the maximum lateness. So it's a min-max problem. We call it min-max. You want to minimize the maximum lateness. So be careful. If I change the goal means that, for example, instead of minimize the maximum lateness, we want to minimize the total lateness. That's a different story. That means you have to add all the lateness together. So obviously, this greedy algorithm no longer work. So it's up to you can think about if I change this objective, so what's the solution? Can you solve this efficiently if you want to do optimal schedule? Right. Okay, so let's just focus on minimize the maximum lateness. So in this example, you have 2 as a lateness. One lateness is 2, another lateness is 6. So this is a 6 is the result. So it turned out that the schedule turned out to be easy in the sense that you just look at the deadline. The early deadline means a higher priority. So you prioritize the deadline. And in this way, you can minimize the maximum lateness. Sorry, I don't know what happened. And so actually the solution is very intuitive. The reason is that you can imagine that you pick any 2, right, adjacent one, like a D1 and D5. D1 has early lateness. This is a late lateness. So you always put the lateness later, right? Longer one. If we do a swap, you will make the situation much worse, right? For example, like this one, for D1, you have a lateness 2, and this has no lateness because the deadline is 14, you finish at 11. If we do a swap, then this will make it even much worse, right? So the lateness will increase. So that's give you the idea is that if you swap something, they're getting worse. So that's why earliest deadline first makes sense, right? So this is a way to prove optimal is that for any solution, means that it's not earliest deadline first, they can do a bunch of swap. But each time you swap, you at least improve the lateness, so getting better and better. Eventually, you get to the one without any, I mean, it strictly follows the deadline first schedule. Okay, so that's the idea. Detail, we probably will not go through that. So this is a basic idea, right? So you sort your sequence based on the the deadline. If you follow this deadline, right, 1, 2, 3 deadline in increasing order, or no, non-decreasing order. So this is we saw the normal sequence 1, 2, 3. If we see a case like I is less than J, I is less than J, but I appear after J, then we call the inversion. Just like the example I just showed you, right? If there's inversion, then you will increase the lateness. So that's the idea, like you just keep on. Whenever you have a sequence that does not follow 1, 2, 3, 4 to n, then you can just do a bunch of inversion, adjacent swapping. Eventually, you don't have any inversion. And when you don't have any inversions, then you get the optimal result. Okay, so that's the another one. And actually the proof is kind of messy. I mean, obviously you want the formality you need. For explanation is much easier. You just do a bunch of swapping, adjacent swapping. That's very important. So you can think a little bit, for any cases that is inversion, you must have two like adjacent one. That's very important, okay? Adjacent one, why is that? Think about that. You can use by counter example. But you do a swap is always adjacent one, swap, 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 okay? So that's the solution. Again, if you read those proof, it's a little bit long, right? And again, the nice things for this book is that they also give you all kind of extension. And this give you a hint, also the idea that when you change a problem slightly sometimes, looks like the same problem, but you make a problem much harder. So in the previous example, we showed that in the interval schedule, you have an easy linear greedy algorithm. If you add a weight, then the problem is much harder. You have to use dynamic programming. And then for this case is that for each job, right, by default, we assume that all jobs are available at the beginning, so you can schedule anytime. But in reality, it's not, because sometimes the job start, we call the release time. For example, I assign some student to do the work, right? For example, today, they say, okay, sorry, the job is not ready. For example, you can proofread one of my paper, but I haven't finished the paper. I can tell you, I will give you my paper to proofread tomorrow noon, but you have to finish by 7 o'clock. Then later I give you another job for programming, right? Or verification something, but the data is not ready. Data will be ready tomorrow at 8 a.m. But I want you to finish by midnight, right? So it looks similar, like each one has a deadline, but the problem, there's a release time. The release time is not the beginning. So in some sense, I give you some kind of flexibility, but not by too much. So they give you a range. When's the earliest time you can start? When is the latest time you have to finish? Right? They give you a range. If the problem is given such a range, then it's an NPR problem. NPR means we'll discuss later. It's very hard. There's no polynomial solution. Okay, so that's then I briefly mentioned that. So the whole field of this is scheduling like a graph scheduling. So lots of interesting model. Right? So if you have a time, you can look at some book like my book. One particular type of schedule is called pipeline model. Like you have assembly line, you have multiple stage, each stage do some work. And this is very popular in data center application like Hadoop, right? You probably heard of MapReduce. That's a multi-stage. Or machine learning also, right? So you have a training and inference. You go through multi-stage of neural networks. So at each, hello? Somehow it's echo. And so when you have like a multi-stages, and its execution time, each stage is different. Depends on the amount of computation and the computation. Right? computation time and also the machine, the speed of each machine. So there are lots of interesting problems called pipeline model. So you have a flow shop, job shop, and open shop. So flow shop is basically you have a bunch of jobs, all need to use the same sequence. Okay, that probably makes sense. Like you have a car assembly line, you have to follow a particular sequence. But in some cases, you can have an arbitrary order. Right? So that's a difference. Obviously, this detail is beyond the scope. So if you're interested in this area, you can take a look. Okay, then we start looking at a couple of problems, if you recall. We see that the one common approach we use is by contradiction. We already see that, right? By contradiction. And later we'll see by induction. Induction very common. And probably you learned this in high school, right? Induction, mathematical induction. You want to prove something general. You start with the trivial case, then you assume k is correct, then you want to prove something k plus 1. And another type of problem we already see this is like a swapping, exchange argument. You have you exchange with neighbor two sequence, then you reduce the inversion. That's the one we discussed just now. And then today we'll discuss two more. Actually, last time we already discussed. When you see a problem looks quite difficult, but if you're careful, you map to a new problem, and the new problem becomes very easy. Right? Actually, there are lots of these ideas used in many fields. If you have a double E background, like a fast Fourier transform. Right? So you see that from one domain map to another domain, the problem becomes easier. So the same things. So this is actually a very powerful tool. But unfortunately, there is no universal way to say that you can systematically map to a new problem. You have just have to have a sufficient insight to see that. And today we'll look at a couple more. For example, accounting method. Means that sometimes you prove something, it's kind of very difficult, but if you introduce some money, it makes things much easier. In fact, the last class I briefly mentioned about a matching problem, right? We go to this matching the accounting method again later. And in some cases, I think a lot of students have experience. And when you try to solve a problem, it's quite difficult. But that's counterintuitive. You make the problem even more general. It looks like a harder problem. And you can solve it much easier. So this is a typical example, classic example, Dijkstra shortest path. So in the Dijkstra shortest path, we'll see just shortly today. You want to find the shortest path between a pair, one particular pair of nodes in a graph. But Dijkstra algorithm, turns out, is not to solve the shortest pair, a shortest path between a pair. It's the shortest path from one node to all the other nodes. If you can find the shortest path for all the other nodes, then obviously you solve the shortest path from one particular pair. Start from the source, same source, but to all the other destinations. Obviously, you can solve one particular destination. So this is a very useful when you try to solve something, you solve more general problem. Okay, and yeah, so and later we'll look at the two interesting things. And that's also a little counterintuitive. In some cases, the problem you have very easy solution, very intuitive, and we explain to anyone, people can understand. But it's very difficult to prove. Very difficult to prove. So that's a problem called optimal caching. Later we'll show. And then another problem is that looks very difficult. Actually, it's really very difficult. But just Dijkstra come up with a very nice algorithm and has an easy solution and easy proof. That's why this is one of the most famous algorithms. Because it's a difficult problem, But he solved it very easy and can prove it very easy about optimality. Okay, so let's continue. Before we continue, any question? I want to pause a little bit so that you can ask a question. Any question? No, let me see. Our old student here. Yeah. Okay, so let's review the first problem last time we discussed. And lifetime problem. Okay. I mean, it's not directly related to our algorithm, but this is also one of the way to prove like optimality or to do some calculation. So if you recall, this problem is that you randomly distribute, you put the 25 ends on the chopstick, and then the ends moving the constant speed, either direction. Also random, right? So each end can move from left to right to left, and their location is random, pure random. The only thing is that when two ends meet, hit each other, they will go backward, change the direction, opposite direction. Then in this case, the two middle ends meet, then this end will turn, right? And we hit the other end. And when this end hit with the other end, then the other one will change the direction. So the result is that this end moving from left to right, and when you reach the end, it falls and dies. Same thing for the leftmost end. Right? So we die. Now I ask the question, actually a question a little tricky, not us, I ask, is ACM ask. So that's what makes it more tricky. It's 25 ends. Why introduce 25 ends? Because he cares about the middle end, which is 13th end. 13th end in the middle, right? It looks like a very safe, means that in terms of secure. So he most likely this end will falls later. The reason is that this end will not fall left or right until all the left end die, all the right end dies, right? It looks like the trajectory for this end is going like a zigzag from left to right to left to right. Whenever you hit, right, change the direction. Then they ask, what's the maximum time? What's the maximum lifetime of this end in the middle? So it turned out to be very difficult if you just solve directly, no matter what method you use. I don't know, maybe someone come up some very nice mathematical tool to solve it. So you have to introduce 25 parameters, and you make some assumption, then do some calculation, right? But in reality, if you change the problem a little bit, you just assume that each end has a hat with different color. When two ends meet, they exchange their hat. Then you pay attention to the movement of hat and not the end. When hat always move from left to right, or right to left. And that also very important is that you set up some kind of, you put a hat on each end, and this exchange. The new problem is a lifetime end is because you have a one-to-one bijection between hat and end. So all you need to do is just calculate the lifetime of a hat. Although we cannot really pinpoint the lifetime of particular X. So that's very important. You change the problem, but we know that the maximum time of a hat, right? So which is from left to right or right to left. So immediately calculate it. So pay attention, we change the problem. But we also change the lifetime of particular end. It's not really direct correspondence. Although when a hat falls in one end, dies, but you don't really map to a particular end. But we know that the maximum lifetime of X, the hat, and so you know the maximum lifetime of an end. It doesn't matter whether the end is the middle or in the leftmost, rightmost. And make it more interesting that you can even calculate the average lifetime. without even mathematics. What mean average? You randomly pick an end, any location, which is not necessarily in the middle, anywhere. So there are 50% of chance going left, 50% of chance going right. Okay, so that's why it's a half of the total length of a chopstick. So in this way, you can calculate exactly what's average lifetime. So this is a very nice way to do things. So the second problems I will give you, I think briefly I mentioned, suppose now, so we have more students. So we have 15 students, right? So we need to divide into multiple group. So K group, suppose like in the fall, last semester. Then you repartition into K+1 group. And in this semester, we assume that each group has at least one student. Now you need to prove that there exists at least 2 students. Their 2021 group size is smaller than the group size of last semester, whatever the group they're staying. So let's just look at example. So the example, in this case, you have 10 students, right? 10 students. So you can partition group in this way. So remember in the Zoom right now, right? You can have like a Zoom meeting room, like a, what they call, I forgot the name, some kind of, you have a partition, right? So you can form a project team. So I can assign student 1, 3 in one group, assign the 4, 5, 6, 8, and 10 another group, then the remaining another group. So this is 3 group. Then this semester I divide this into 4 group. When you divide 4 group, you don't really care how, it has nothing to do with the previous assignment. For example, this assignment 1, 2, 7, 8, 4, 6, 9, 3, 5, 10. So what this really means, it says that you can always find 2 guys. Actually is a green color, or not green, a blue color, like a 2. 2, so this semester is 2 guys in the group 2. But last semester, he or she is in the group of 4. So that means this group size is getting smaller. Same reason for 7 and 8, right? 7, 8. 4, 5, 9. 3 and 5, let's look at 3, 5 is not, because 3 stay in a smaller group last semester. 5 now is a 3, also in a smaller group. But 10 is not getting small. Now it's a smaller group. Used to we have a group of 4. You see the problem now? So the challenge is that we don't know the partition, how you repartition. There's nothing to do with the last year partition, this year partition. How you prove that there are at least 2 students whose group size is smaller, not 1. So I gave this problem to my PhD student. I mean, someone did it, someone didn't. So most students will use the pigeonhole theorem, right? Pigeonhole means that suppose you have like 5 balls, you have 4 boxes. So you can pick, you put all this ball in the box, at least one box has 2 balls or more, right? But it turns out this pigeonhole method doesn't work here. You can try. So that means the tool you use is not good enough. So what's the tool you use? So this one, we call this accounting method. That's a very nice way. So we assume that we give $1 to each group. That's the key, $1. So in the previous example, you have 3 groups. So I gave out $3, right? Then when a group will get $1, they will be evenly divided among the group member. So that means this one will get what? 15 cents, 50 cents, 3 will get 50 cents. In this group of 4, then each will get 25 cents, and so on. So the same things for the group of 21. So you have $4. So each will divide, right, equally. Now this is the key. What's the difference in total dollar in 2020 and 21? It's a $1 difference, $1 difference. Right? So then you can just prove by contradiction. Right? So just look at a very simple example. For example, let's look at the 3, right? So yeah, or 10, just look at 10. 10, how much money that guy will get this time is 1/3, right? That's 1/3. And last semester you get 1/4. Okay, 1/4. So what you need to do very simple math. You subtract the money this semester by the last semester. That's the difference. What's the difference? If you subtract, it will never be equal 1. It's always less than 1, strictly less than 1, right? Is it correct? You pick any because group size is 1 or more. So whatever each member receive is less than 1, and you subtract something which is less than 1, it will not be equal 1. So then you get the result. Why is the result? Because totally you have $4 assigned to 2021, $3 to 2020. Right? So you need at least 2 guy has a larger number than last semester. So that's solved the problem. So it's a very elegant way to prove it. You don't even need the math. Maybe you need to just elementary math to officially prove this difficult problem. Okay, so this is the problem. Now let's go to the exciting problem I gave you last time. By the way, I also revised the slides so that you will see this one. By the way, anyone think about this and solve the problem? Now you can get some bonus. Right. So let's again look at this matching theory. By the way, this is a matching theory. It's something like a game theory. Why you think this matching is like a game? So you have like a 2-sides game, right? You have boys and girls. They all try to take the control. Means I want to find the best guy. I want to find the best girls. So it's some kind of like a game, right? So that's why we have Gail Shafferly's famous algorithm, stable marriage. By the way, it's interesting that only one guy got the Nobel Prize. The other one guy just died. It's very sad. Actually, he died recently. I forgot, it's like 10 years ago. And they have to wait like 50 years or 60 years. 60, I think this one invented a long time ago, yeah. So Shapley wait for until 2012 before receiving a Nobel Prize. I think he proposed this 60 years ago, that algorithm. And Gail's a little bit older, I think only 3 years older than him. He just died. Then he never got the Nobel Prize. You know the rule of Nobel Prize, you cannot award a prize to someone dead, no matter what's the contribution, right? So it's important to live longer, hopefully something good will happen, right? So this is the, but now we last time we discussed a little interesting problem, means how can you come up some kind of mechanism design? We call mechanism design, or mechanism design you can imagine like government policy or whatever, the algorithm or rule, so that you can get some kind of property. So we look at the one extreme case, like a new president have some kind of new rule, says that let the woman decide everything. It's called like we call this one-side domination. So how can you rearrange your marriage so that all the girls are happy, getting what they want? Also, they try to avoid the internal fights. Right? So all these things, there is some kind of mechanism design, means that you need to satisfy some kind of property. So the property they discuss, oh, by the way, I put some of the reference. So the first one, that's the one I asked you to solve, is actually proposed by Gale, David Gale. So he really make all this contribution. So it's written by a chapter in Shapley and co-author. But he credited this all the algorithm based on David Gale. So properties are very important, especially dealing with the game or any economic model, right? So lots of students who are doing this economic model involve lots of mathematics. In some sense, kind of sad for mathematicians and computer scientists. They never have a chance, no matter how good they are. They never have a chance to get the Nobel Prize, because Nobel Prize only for economics. Although all the works is algorithm and the mathematics. So let me just quickly talk about this property that's interesting. One property called strategy proof. Strategy proof means that quickly is that whatever the mechanism or algorithm proposed, it should be strategy proof means that no one will lie. No one will lie. Can you imagine? Can you come up some kind of property that no incentive for you to lie, because you will not get extra thing if you lie. Think about this one, right? Can you imagine a society, a government, or you rule, you can come up some policy. If you lie, you will not get better or you get severe punishment. So this is called strategy proof. But put in a simple way, is really that when a girl tried to do some kind of exchange, the girl will never lie. Lie means I prefer another guy than my current partner. What happens if a girl lies? Lies means that in reality, I prefer the current partner than the one I really want. Will she get any benefit? Probably not, but you have to have official proof that. Another one is called Pareto optimal. Again, Pareto is named after famous economics, also like a mathematician, so optimal. So what means optimal? You can, because optimality is not unique anymore in the sense that we see the example, right? Lots of girls may prefer a particular guy. So what means optimal? So eventually only one girl will match to that guy. So you may have a many scenario, right? But optimal in the sense that you have lots of exchanges, and so you keep on exchanges, your quality, whatever, your satisfaction is always getting improved. It will not getting worse. I mean, you cannot let the situation happen like one girl profit and the other girl suffer. So everyone getting improve until no one can improve. So you reach what you call the Pareto optimal. Although you may have a lots of Pareto optimal cases. Right? The third one, it's all kind of important in the game theory, or actually in any community, really like, it's like a collaborative game or something. Really means that what's the incentive? Individual rationality means that why all the girls want to involve in this kind of new exchange or swapping things, because their benefit, their profit will not suffer. They can only benefit, will not suffer. So that means people are rational. Rational means that I'll participate in this game if there's only a game, right? We never lose. A unique core allocation, but this is a little bit more involved in just to show you in this case, there is one solution, only one solution for that. Okay, so let's just look at the algorithm. The algorithm turned to be very simple and very natural. So just let each remaining woman, just I say remaining, initially everyone participate. Point to her favorite remaining man. Initially all the men are in there. Reallocate is suggested by directed cycle. We'll talk about direct cycle later, including self loop. And delete the reallocated woman or man, or other woman kept the current current man. Just continue. Let's just look at the simple case. So let's look at the left-hand side, right? So the 1 to 3 represent the girls. So making the decision now. Each girl has a preference. So 1 means 3 first, second, 4, then 1. But for girl number 2, prefer 4 first, then 1, 2, 3. Then the diagram shows it's a current allocation, like a stable marriage, right? So assuming you have a stable marriage, means that 1 mapped to girl 1, husband 2 mapped to that, husband 3 mapped to that, and mapped to that. So you do this trick, is that you assign the husband to you. So this arrow really means that husband has no right, just let the girl decide. So you can start any point. Suppose you start at 1, right? So the algorithm works that simple. Is the girl 1 will point to the one, her favorite. What's her favorite? Look at the table. 3 is the favorite. So this one will point to 3. Then the husband 3 say, sorry, I cannot make a decision. I let my wife to decide. So point to wife. Then this wife 3, look at table. Sorry, I prefer number 1, husband number 1. Then husband number 1 says, I cannot make any decision. Talk to my wife 1. But this is the source, right? So you form a loop. So what does loop mean? Think of it. Loop really means a swap, right? So all you need to do is just a swap. So 1 and 2, 1 and 3 swap, then you're happy. So once you swap, you can remove. So that's the key. Once you swap, you remove from the competition. Then the remaining one can continue. What's the remaining one? 2 and 4. Okay. Then in the 2 and 4, so that's key. Once you removed, your priority list also removed. Now you have only 4, 2 left, right? So although in the 2, 4 is still number 1, that's great. For the 4, her preference, number 3, already gone, no longer available. So she can only settle for the number 2, right? So you repeat the same process. You repeat the same process, you form another loop. Okay, then it's done. Now, I'll ask you to prove that one. Why this is Pareto optimal? So obviously, the proofs are beyond the. So the key is that you first go for the first guy, then you eliminate all the loops, then you clean the table, make it smaller, then you go for the number 1 in the new table. Just discontinue, continue. Now, what's the complexity of algorithm? It turns out the complexity is so simple, it's linear. Why is that? The reason is that, see, this is very important. Means that for each one, you start with a woman, you seek someone, or could be like there's some extreme case. This woman turned out to be my current husband is a favorite. So what that mean? It's like a self loop. If a self loop means what? Just take out. You're not in the competition. You're very happy, right? So no matter what, each time you just continue, you continue, and eventually you will form a loop, right? You form a loop. So that's why this is kind of linear solution. So any question on that? So you see, this is a very nice algorithm.
Professor, I have a question.
Yeah.
I think that this is for the scenario without money. It means that each of the edge has just, for example, unit cost 1. But if we have to consider money, so that we need to consider different weight for edge and try to find the loop or cycle with maximum flow.
Yeah, no, but it's slightly different. We're talking about a situation about money. Right now, it's no money, but it depends on how you deal with money. Money means that, since you bring out the issue of money, so really it means that you look at all these boys, they suffer, especially their parents suffer because they raised 20 years, so they don't have anything, right? So you may marry someone, very poor girls with no money, life will be very miserable. So that's why later we introduce some kind of money. Right? So we'll see the
Yeah.
next algorithm. Right? So this is a totally different problem. So you get that one? And remember I mentioned that I make things more difficult, although it's not in the original algorithm, is that suppose you, Penn professor, our neighbor, remember the president's office assigned this to Temple, so I assigned to students to solve. They say that this is not ethical algorithm. What means not ethical algorithm? Is that you see that there's a big database, big data, one big data. You see all the girls' data, right? On the right, left-hand side, all this their preference. So to run this algorithm, you have to have all this data. And I'll see all this data. So how you respect the privacy of the girls? So how can you run the algorithm without knowing any information of the girls? Is it possible? Think about this. Is it possible? By the way, the Gail Shefferly's algorithm is possible, right? So order just say the man just proposed someone. Obviously, the girl who get proposed knows the guy's intention, but nobody else. At least keeps that kind of privacy. Can you do similar things here? Can you do similar things? Without collecting the database, without collecting the big data. So we're talking about 40 million girls data and 40 million guy. So the table size is 40 million times 40 million. It's too much. In fact, this can be run without any data. So that's really interesting. Actually, I already gave you the hint. Really, when I explain this algorithm, I start with any girl. This girl is number one. So this goes, well, what's the step? She just proposed to this guy, right? You just send a message with your ID in there. Or later we can talk about it. You learn all this security. You can encrypt it. Then this husband just passed this ID to the wife, number three. The number three will continue the same process, go to the other one. You piggyback your ID. Right? It's like a sequence. Right? Then whenever someone receive it, you need to check, is my ID inside? If my ID is inside, means what? Already come back. I'm part of the loop. Then you do the reverse way, right? So I'm not going to go to the detail. There are obviously other things. So this is a very nice way. But you may ask,
Professor,
yeah.
I have a doubt, like how is this linear actually? Because if we start at number 2, then again we go to the 1 and 3 cycle, right?
Yeah. No, linear in the sense that, no, suppose you start one at a time. So one at a time really means that this one, right, from
Okay.
one, eventually match four, match three, right? So it's
Yeah.
two step.
Yeah.
Each step times 2. So it's a linear. You delete
Okay.
the 2, right? You delete 2. You use the
Oh,
4th
okay.
step to, so it's 2n.
Okay, you remove that. Okay,
Yeah,
yeah.
you remove, then you reduce. Each
Yes.
time you remove. By the way, this is cycles. This cycle is not necessarily 2. 2 people. You can have 4 people, 5, whatever number. Cycle could be very long, right? You see, that's very nice. You can have A to B and B to C, C to A. So you have like A, B, C, D, A, all that kind of things. So you understand that?
Yes, Professor. Thank you.
But one thing I want to just briefly mention, it's kind of important. The example I gave you is kind of ideal because you're the originator, you're a part of the loop. There's some situation you're not part of the loop. But that's very easy to explain. So suppose the 4 start, right? 4, look at the 4. 4 says I prefer number 1 or number 3. So 3 says, sorry, I go to number 3, right? My wife 3. 3 I go to 1, 1 go to 1, 1 to 3, right? So this one is not also involve a loop, but it's in the middle, not necessarily the first one, which is okay. You understand now? So in this case, still you remove the 1 and 3. So 4 just initiate. So not necessarily involve the loop, but eventually you just keep on going, you form a loop. Not necessarily the loop of involve everyone, but at least a small part. Then you just remove it, right? So any question about that? All right, so no question, let's go to the more interesting problem. Again, this is invented by Gale, Professor Gale. So this is one of the problems about the money. So the boys' side say that, sorry, if you want to marry me, you need to give me a certain amount of money. So this is the algorithm we discussed a lot. And this I put you see that this is relatively recent, 1986. So it's 24 years ago. Right? So it's like an auction. Right? So the idea is the same. Imagine this buyer is a girl, this is a boy. Now the difference is that that's also very interesting. That's a real total market. Really means that you can imagine this boy is a commodity. So each girl value the value of each guy. So girl one think that this guy was $12, and then the second guy is $4. You can say million. Okay, make guy feel better. Then the third one is 2. The girl number 2, I think the number 1 was of $8. Then $7, $6. This means that all these 3 girls are guys are very similar in her view. So he's willing to pay that. I mean, again, everything is relative. But the fact that they're willing to pay that money doesn't mean that the guy will eventually get the money. Depends on the market. So how it works. Right? So you can see that from this particular example, by the way, last time the example I gave you is kind of wrong. I cut and paste the wrong figure, but this is correct one. You look at the A, right? So A, somehow I have a problem like, all right. So this guy will propose to, or this girl proposed to this guy. Everyone proposed to the same person. So that's the key. This means that the guy A is marketable. Is that right? So what's a normal life? It's where lots of girls propose me, say that I must be very popular. I'll raise the money. So whenever you have I'll raise the money to $1, so 1 million, okay, whatever. Then when you raise the 1 million means that if you want to marry me, you have to pay $1 million. But then look at this changes. Why is this change for Y in the second diagram? Because Y, in Y's view, what value of A and B differ only by 1 million. So if the guy A asks for 1 million, B asks 0, what does that mean? They're equal. So for guy's point of view, you want to find the best in terms of reward or whatever. The reward means that your value minus the cost, right, or utility. By the way, this is a very important model in many fields. So the guy will think that I can propose either A or B. Either A or B. Right? Then all the other one never change because in the view of X and Z, A is much, much better than the second guy. So they all still go for this A. But assume that this is honest. A realized that now girl Y is wobbling, right? It's like undeciding. But still I have two girls proposing me. I keep on raising the money. So this guy will raise another $1, 1 million. You see the difference now? Yeah. So after this, the money is raised, then the girls Z change mind also. Did you see that? Then the girl Y totally changed. Means that I'm not going to propose you, I will propose to B. Do you see this one? But then the D, why now look at the difference. The difference is that B is marketable. Type B marketable because why? Because Y only proposed to him. So he can really raise the money, right? So that's why he raised $1 million. Once this one weighs $1 million, right? So you see this the whole situation, right? And the A also still raised $1 million. Why can raise? Because although I have only one really, X is still very serious, only proposed to me, so I can raise $1, $1 million, so raise to 3. Then what you need to do is that you have a central entity. You look at whether you have a perfect match. Perfect match means that you can have a guy and girl, just whenever there's a line, you perfect match, you stop. Right? In this case, A match to X, right? A match to X, then C match to Y, B match to Z. Is that a nice algorithm? It turned out this value, the final value A gets, called the market clearance value or clearing value. That's your real market value. Just imagine this, you sell whatever apples and that. So that's the way market work. But this one just solved this stable marriage problem. But it's different, it's like one dominate. But what you want is to give the other side some money, right? Although this money can be said it's a fake, because when you marry, the money just belong to you anyway. Okay, so this, you see that this is a really interesting problem related to matching. So 2 variation. Any question? So you guys spend too much time on this, but let's continue then. Before we take a break. So we will discuss the remaining one and finish this chapter today. Oh yeah, this is continue. Right. So let's continue with optimal caching. That's the example state that its problem is very easy to solve, but the proof is very difficult. Let's first look at the problem. The problem, in fact, is very realistic and using in the memory, right? So cache, we know that you have a faster memory, which is very expensive. So that's why you cannot build a very large fast memory. So you have a concept of memory hierarchy. Right? So that's the whole, like when you learn computer architecture, actually in everything, even network caching and all that. So the idea is that you want to put the more frequent access data close to you in a faster memory, and less frequent one you put in the other ones, a slow memory. So we learn all this from the operating system is have a cache hit, cache miss. So that means if you access this memory, which is cache, small one, if it's already there, it's nice. So you get it, and it's very fast. But in some cases, in some situations, depends on percentage, you will miss. If you miss, then you waste lots of time because you have to bring in the requested item in the cache. It takes some time. And you have to evict some existing one. So the key thing is which one to evict. That makes things harder, right? If it's full. So let's just look at one example. So suppose you have a cache of 2 units, and you have a request sequences A, B, C, B, C, A, B. So what's the eviction schedule? So the best one is that you see this red one, you evict that one. So you put the A first and B, right, A, B. Then when you have a C, now the question you need to decide whether you evict A or you evict B. You need to remove the A or B, right? So in this case, you remove A, then you have a C, you still hit, or B is there, then C hit, then nothing. Until you have another A comes later, then you miss that. They will replace, now the question you replace A, B or C. In this case, remove C. So you get only 2 misses. In this case, that you do some simple math calculation, you will say, oh, this is a minimum cache miss means a minimum execution time, because each miss will cause extra time, right? Now the problem is, what's the optimal way to do it? It looks like very difficult, very difficult. It turned out that's really surprising. There is a very nice algorithm. It just says that it's called furthest in future. So in this case, let's just look at this example. Furthest in the future, when you have a cache miss, you need to evict one item, right? In this case, A, B, C, D, E, F. Which one you want to evict? All you need to do is see when is the occurrence of each item. For example, A occur the next one, so very early. B is the second one, then C, right? Then D is a little bit later. F will come the latest one, right? Very late. So all you need to just evict F. Just take out the F. Okay. So does that make sense? So it means that obviously this assuming that you already have a knowledge of a future queries. In reality, you don't have that information. So that's actually the challenge in all this cache replacements policy. Just be careful, right? So you don't want to get the wrong conclusion, say, oh, doctor told us that there's a best replacement policy. Why in reality, everyone uses a different type of replacement policy. The fact that this one, assuming that you already know the future, but in reality, you have no knowledge of future. In the current one, you only use the past information, not the future information, right? So pay attention. This one is like a future. If future already know, you have an optimal replacement policy. Any question on that? So the proof is very subtle. I'm not going to go through the detail. I encourage you to just read it, because if I want to spend this proof, probably need 1 hour. Actually, proof quite involved, and you probably get lost anyway. So the idea is very similar. It's also kind of idea we talk about like inversion, right? Swapping. You have also some kind of idea of a swapping, and it's in here is a swapping decision. Means that whatever the other way the decision, you can some kind of swap, then it's no better than this approach. They eventually prove this optimality. So I will skip all this one, because to prove this one, you have to have also, they have to introduce a new concept. But there's one important concept is this one. Means that, and probably students already observed this one. Should you bring something before it comes? So that's called, it's very important concept, right? So in all the previous case is that only when you have a miss, that you bring that element. Now the question is that, can you bring something in advance ahead of time? It turns out you bring ahead of time will not get better. Okay. So this is one of the important observations. I'm not going to go through all this. It's very involved. Look at the proof, like multiple pages. So that's but I want to really discuss with you some of the important things. I'm talking about the optimal solution if you know the future, but in reality, you only know the past. Right? So that's why you have all kind of learning. Right now, it's like a hot topic. Learning really means that can you learn something from the past? You can predict the future. So all the eviction algorithm or replacement algorithm based on the past. So one algorithm called LIFO means evict page brought in the most recently. So you think why you kick out the guy who just recently. So this is under assumption that since this is recently used, the likelihood this will come near future is less than the other pages. Right? That make sense. Suppose this you have to assume that what kind of the distribution. Imagine if all the pages are uniformly distributed, probably that makes sense. But the problem is that those item comes random, right? So now the question is, can you learn this pattern or distribution of each item? And hope that those distribution will be relatively stable over the time, not change dramatically, right? So that's the key assumption. If you want to use past data to predict the future, you have to assume that there's some kind of stable state or whatever, relative stable means that the distribution is relatively stable. Okay. And another one is that most popular one, surprisingly, is LRU, right? We all know when someone talk about cache replacement policy is least recently used. Okay. So let me evict the page. Oh, what happened? Evict the page whose most recent access was earliest. Long time haven't used, the likelihood this will be used in near future will be small. That's the assumption. Right? So all this study is kind of very involved, but there is one surprising result. If we have a time, we'll discuss. Use some kind of randomized solution, you can prove that LRU is competitive. Competitive means there is some kind of bound compared with the optimal result. And this actually is a better version through random caching. Random caching really means you randomly evict one guy. And the LRFO can be arbitrarily bad. Right? So that means theoretically it's not really great. Okay. So that's the one. By the way, I haven't talked about online or offline. That's actually basically what we discussed. So offline really means that the full sequence of requests is known a priori. Really means I already know this one. If everything's known, then it's easy, right? So that means you know the future. But in reality, it's online. Online means that you not know in advance of the future request. That's why we have to rely on the past information. Okay. So you can see the importance of algorithm. We use all these things in the operating system, right, or computer architecture. So all this involved algorithm and analysis. I think it's a time for us to take a break, and we will come back at 7 o'clock. Okay, let's get started. So after the break, we'll talk about two more algorithms. The first one is the shortest path algorithm. Probably all of you know this. And this is probably the most famous algorithm in the world, invented by Dijkstra. So he's a Turing Award winner. So this is just one very simple example, but this one shows the location of Princeton CS department to Einstein's house. What's the shortest path from one end to the other end? Or you can imagine that from Temple, main campus, to airport, what's the shortest path? So this problem is some kind of unique in the sense that, as I mentioned earlier, in order to find the one like shortest path, it's better to find shortest path from all of them, to all the destination, not just to one, to all the destination. And so it depends on where the source. Source is one, right? So you want to find the shortest path from 1 to 2, 1 to 3, 1 to 4, whatever. You need to find all of them. And during that process of finding all the shortest paths, you will find the shortest path to 2, the one you really want, and the process is stopped. So this is based on some kind of greedy solution. So I think the best way to describe this is, let me see if someone told me that you can switch the audio. By the way, I cannot see my audio to see if I can, yeah, maybe this work. If I draw something, hope you can see. Depends on how I should orient this. To see if this work compare with, oh, it doesn't work. Somehow it's not clear. Let's see, try it. Can I even see my hand? Probably I should set up ahead of time. It's more difficult. Yeah, maybe. But the problem is I don't see you can see it.
Professor, I think that if you stop sharing, you can see better.
What?
If you stop sharing your screen, you can see better your.
Really? But this is a sharing. You have to share.
No, your screen is sharing. If you stop sharing your screen, I can see you better.
Oh, so you mean stop sharing? Like this?
Yes.
You can see better?
Yeah, we can see now in a big size.
Oh, bigger size.
You can swap it in Zoom in the camera. You have the option to swap between the screen and that, so it doesn't really matter. The quality is the same.
No, quality is the same. Yeah, I think I need to. Yeah, that's more difficult. Yeah, that's unfortunate. Actually, this one's the best way to describe is a draw diagram. Or maybe I can use other screen. Okay, let me see how should I do it. But then the problem is but then I need to write in the, that's more difficult. Okay, so I think I'll give up. Maybe I'll try next time ahead of time, test it before I do that. So the key thing is there is a concept. Actually, it's a color scheme. If I describe this in a color, you draw a diagram, it's much easier than the algorithm described in the book. Although it's the same idea. So let's just follow the, you can see now, right? So let's just first describe the algorithm. Is that suppose this is S source and T is the destination. You have all the roads with cost. So you want to find a shortest path, means that a path with a minimum number of delay. You just add age weight together. This is minimum. Now the question is how you find out the minimum one from S to T. In fact, the best way is that you have a concept of like you start with S, then you grow. Again, without drawing it, so it's very difficult. Yeah, so we can do, I think probably you can do that. So the idea is that you explore nodes, you maintain a set of explored nodes. So you can imagine this is here, S, start with S. Then you explore your neighborhood. So the first step, you include all the neighbor of S. So this is called the explored region. Right. So that's eventually you expand and expand. By the way, when you check all the neighbor of S, you want to find the one which is the shortest distance. Then you include one node in the explore region. Then this explore region has two nodes. Then you examine this explored region to the boundary of outside nodes with one connection to one of the nodes inside the explore node. So we call this color. Color means that the nodes inside, we can call this black node. Then the boundary between this black and outside boundary node called gray node. Then still the outside one is called white node. So it's like a three color. Then among the gray nodes, you find the one that the closest distance to S. Then you include that gray node in the explore set. Then this node become black. Then that means you expand the territory. When you expand the territory, some of the white node become gray, means it's in the boundary between black and white, we call gray. So this algorithm is just working this way. It's very simple. So let me repeat again. Initially, you just include one node, which called S. Right? Then you repeatedly choose an unexplored node. Unexplored node means it's on the boundary between this S and the outside. You pick the one with the minimum distance from S to this boundary node. But how you calculate that, it's iterative because you need to find out the distance, right, from, in fact, you need to maintain some kind of distance from S to a nodes inside this territory, which is a DU. Then the one you connect to outside node, this we call gray node. You add this one, that's the distance between S to this particular node. Then same thing for this one. And for this node, you also have estimate distance from S to this inside one. You may have several connections. Then pick the one with the smallest one. That's your current estimate distance. Then each round, you pick a one at a time, include that node in this explored set. When this node included, they change from gray to black. Then this area exploded, right? Then the boundary node change also. some of the white node become gray. Then you just repeat. So that's it's that simple. Again, I apologize that without drawing, it's very difficult to describe, although everyone knows that. But using color is the best way. Any question about that? You probably learned this algorithm like many times. Okay. Oh, actually, there's some diagram can show this. Can I go back? Why this doesn't work? So this will go back. Oh yeah. You see this how it expand, right? But this is not a good example. It does not show the color. It does not have a white color one. So in this case, outside nodes are all gray because they have one adjacent link to a node inside. Right? So that means all three nodes outside is a candidate. Then you pick a node with the shortest distance from S to through this one of the node inside to this outside node. Then that's the one. Suppose V is the next one selected. Then this area increase, right? When they increase, then the outside node set also increase because there's some maybe another node here very far away. Since this one node increase, so this may have a neighbor connection. Then this become gray. Gray means it's a candidate set. Then among all this outside gray one, pick the one with the minimum distance to S. Then this continue. So it's a very simple, but it's not a linear algorithm. The reason is that there are lots of connection, right? From the gray node to the black node inside. And you may have multiple choices. So that's why you have to go through it. So we'll talk about later about all the data structure you can use to implement that. Okay, any question about Dijkstra's algorithm? If not, maybe I can, since on this page, I will discuss another one. This approach is actually used in many algorithms. Let me just give you another algorithm. It's the same algorithm, but it's used for different purpose. So you probably know the Prince algorithm for minimum spanning tree. What's the use of minimum spanning tree? You can just imagine that each node in this one is like a house. Like a house. Imagine you have a cable company. Your job, cable company, is to connect all these houses. So that means you want to find a tree with a minimum distance or accumulated distance of edges. So how you find that? Actually, you can use the same algorithm as Dijkstra. Probably not many people say these two are the same. It's basically the same idea. Is that you start from the one beginning one, S, you keep on expanding. The only difference is that each time you select the neighbor, you just select the neighbor, the edge, not the distance to S. The weight of the edge means connecting a gray node to a black node. So that's very simple, right? So that's the step. You just pick an edge with a minimum weight among all the edges that are connecting between one black, one gray node. So when you expand the territory, some of the white node has a member of a neighbor with a black, then white node will change gray. So you just repeat the same process. You continue this process, look at all the edge connecting black and gray, you pick a one minimum value, and you keep continue. So each step you add one link. That means you add one node. After a certain number of iterations, you construct a spanning tree. So that's a famous, also called Prince algorithm. I'm not going to discuss this Prince algorithm, although it's in the book, but it's so simple because it's the same like a Dijkstra algorithm. And there's another parallel version of Prince algorithm called the Cruscourse algorithm. Right? You also discuss that in the regular data structure or algorithm one. So conceptually, it's like you can, instead of this centralized start, grow a tree from one source, you can grow a tree from multiple sources, eventually merge. So I'm not going to discuss in detail about this merging process. So the same idea, instead like you grow in one area, you grow multiple area. But when you grow an area, you may merge multiple regions. And just be careful when you include one link, you still add one link at a time with a minimum cost. But you cannot add a link that will create a cycle, right? That's a tree cycle. So this just keep on adding. The difference is that instead of growing from one, like a connected component, you can grow anywhere. You can merge multiple components. Eventually, I mean, each component is a subtree. Eventually, you form a global tree. So that's a Kruskal's algorithm. Any question on that? Now you get the idea of this greedy algorithm. Any discussion? It's very important, this kind of algorithm. And now I hope you can get some general idea. This idea, okay, sorry, I cannot write on the board, is in the distributed algorithm called the wave algorithm. Wave. What I mean wave? You can imagine that the area grows, right? It grows. It's like a wave. And you have a frontier concept, like a frontier. So frontier is the one that the gray color, which is adjacent, connecting to a outside to inside, right? You understand that? So this broader area, or this gray area, is the area that you further expand. Then you pick one particular node, satisfy certain condition. In Dijkstra case, Dijkstra algorithm, is the shortest path from this gray node to the S through intermediate nodes through this explored nodes. Explore the node. That's very important. This the whole cycle inside. Then you keep on growing. For the Prince algorithm, shortest minimum spanning tree, it's the same idea. The difference is that the selection criteria is different now. You select the edge, one particular edge that has minimum weight. It's not the distance to S. Right? So you can imagine those like a wave going. Eventually wave cover the whole area. You can imagine now it's like a virus spreading. You keep on spreading, increase territory, cover everything, you stop, right? In fact, this is very important, is that as you grow this area, grow this area, right, grow, and you find the shortest path to all these nodes inside. So when the algorithm should stop, it should stop when this area, explored area, cover the destination area, you should stop, okay? And in fact, there is some kind of acceleration. You can probably already can guess. So this wave or this exploded nodes area, why don't we just do in both way? Both way really means that you start from S. Can I start from D at T from destination? You can do that. Actually, you can do two at the same time. Both sides grow until it hit. Once it hit, you find the shortest path. So basically one from S to an intermediate node, another one from destination to intermediate node. To get that. So there are actually some interesting extension of Dijkstra algorithms. You can have like a two version run, one run at S, the other run at T, and you stop. Usually, although asymptotic complexity is similar, but if you do two version, usually it's faster. Okay. So now how do you prove that? In fact, it's turned out to be very simple proof. Again, if you read this, it's very messy. So the easy way is to prove by contradiction or by induction process. So or maybe we just read this one, so you see if we can get that one. So you're doing induction process. Let V be the next node added to S, and let the UV be the chosen edge. So this is one. So this is actually the step that you're growing, right? It means that that's the shortest one in terms of distance. So then it says that the shortest path from S to U plus UV. So use this the induction process. Induction process means that suppose this is already the shortest, S to U, you add that it's still shortest, but you prove by contradiction. So consider any other S and V paths. You may have a multiple paths for SV. And we will see that if there's no shorter one, compare with the one goes through U. And let the X and Y be the first edge in P. P means inside. That leave S, P outside, sorry. Leave S means it's explore the set. And let P prime be the subpath to X. So this is the path to X. And P is already too long. Actually, so you already exit this region. Remember this greedy solution, you always pick the one with a minimum distance going outside, right? So the key is minimum distance from S to going outside. For any other paths that you leave this region and going outside, the distance between S and Y compared with distance between S and V, SY is longer than SV. So that's how you prove. Okay. So this again, you can just think about that. So the key thing is that if there is any other one, it must be leave early, which will cause contradiction. I mean, not going the other path, going exit this region, it will be longer. So this is the simple proof. So let's just think a little bit more about this one. So in this shaded region, so you build a kind of tree, right? Shortest path tree. Then you keep on adding one at a time from outside. That corresponds to the next shortest one. And using the nodes inside this region as intermediate nodes. Right? So that's the idea. So that's a greedy one. Then you just keep on finding. At each round, you find you find another node with the shortest path. So you build the shortest path upon a set of nodes shortest path. And this is a good example to show that it's better to solve a more generalized problem than solve one specific problem. So that means to find the shortest path to a particular destination, it's better to find the shortest path from a given source to all destinations. Then along as a byproduct, you find the shortest path to a particular destination. Although this algorithm will stop as soon as the destination is included in this set, not necessarily you have to find the shortest path to all the nodes. Likely it will not, depends on the shortest distance, right, between S and the T. So that's the algorithm. Okay. And a little bit about data structure, just like refresh your memory. And this will give you a good example. In fact, Dijkstra's algorithm probably is the most famous one to illustrate the importance of a data structure. Because if you use different data structure, you may get a different complexity. So in this table, it just shows more detail. So like how you support a particular function in a data structure, like insertion and change the key value, right? Extract minimum, usually it's a heap. You take out the minimum one, Why you need to take out the minimum? Because you know that in each iteration, you find one minimum value, nodes with minimum pass. So it will be included from a change of color from gray to black. So that means it will not be the candidate for the next run. So that's why you need to take out the minimum one. So this is how you update, right? And the change key is also important. Really means a distance. It's a distance from source to an intermediate node. You keep on changing as you add links. So these are like a key operation. And you learn in data structure and algorithm, heap is very useful because it's a special type of tree that can easily maintain the minimum value. Although it's not a really sorted sequence, but minimum value is very easy to get. And in fact, probably I think you already learned, right? Yeah, maybe I can ask this question. Anyone learn this Fibonacci heap? Yes or no? Anyone heard of?
Yeah, it was covered in programming techniques, I think, in the previous semester.
Yeah, okay, so that's good. So you know Fibonacci numbers. So it's a special type of basically, you have like a multiple sub-heap, multiple heap connecting some ways. Right? It's named after Fibonacci, a famous mathematician. Okay, so this, but you can see this complexity changes. N is the number of nodes, M is number of edges. We know that maximum number of edges is N squared. It's like a dense network, means that in a graph with lots of edges. Just be careful that, actually if you attend today's talk, seminar, so I invite a famous researcher from University of Vienna, right? So he's talking about all kind of a new interconnection network called dynamic adjustable network. So this the performance sometimes depends on the density of the network. Just like a big data, so each network can be represented by a matrix, right? Whether it's a sparse matrix or dense matrix. So same thing is that which data structure you use to implement Dijkstra algorithm depends on the density. Okay, so that's why you can see the difference. Some is measured based on nodes, some measured based on the m times log n. But m could be, it's a variable, depends on the density. Small density is n, right? It's tree. Tree has only n minus 1 links, but it's very, very dense, then it's close to n squared. So sometimes better to use edge number to measure. Right? So you can see that the performance varies, depends on density. So there's no universal best data structure. So it depends on the density of the graph. So again, I assume this all covered in the data structure and the program technique. So that's for this algorithm. Let me take a look. Oh, we have a half an hour. That's perfect. So let's look at the one more interesting thing, like a real life example. Next one. Oh, by the way, this is the one that I also included in your slides. Dijkstra algorithm looks very well, right? But this, you have to assume that you have a global information, very important. Like if you want to decide the shortest path from temple to airport, you need a map. Map really means that you know all the traffic information, road condition. So this is called global information. There's another algorithm called Bellman-Ford algorithm. I think you already know. So it's kind of distributed iterative algorithm. Really means that you don't really need each intersection, I mean each node, intermediate node, doesn't need to know, or source doesn't need to know the topology. Just each node maintain a routing table, which is the best estimate to each destination. So idea is simple, is that each node asks the neighbor, based on neighbor estimate, you adjust your estimate. So it's like a table iteration, just update your table. After that, you find the shortest path. It's a very nice distributed algorithm. Unfortunately, to describe this, I have to use a board to describe. So Dijkstra basically is global information. Bellman-Ford is the distributed, and you don't need the global information. So it's just building a table iteratively, update the table, it converges to a shortest path eventually. In fact, there are two famous algorithms in the internet. One is called OSPF, called Open Shortest Path Algorithm. And based on Dijkstra algorithm. Another algorithm based on the Bellman-Ford, you find it's funny, right? ISIS, that's exactly the ISIS, it's not the terrorist ISIS. This is much ahead of the other ISIS. So this is proposed a long time ago. So there are two, if you want to know more details, so you can look at the internet. So in the really internet routing, they have two separate versions of routing for shortest path. One's Dijkstra and one's Bellman-Ford. And there are lots of debates on which is better. I just cover in my other class, distributed algorithm or distributed system design. So I'm not going to discuss later. Similar algorithm already mentioned that for the minimum spanning tree, and you can use the Prince solution for minimum spanning tree. Similar idea as by Dijkstra, you grow, explore the node set. Difference is that instead of shortest path from source, you find the minimum edge between the black node and gray node. Right? So that's the. So let's look at one practical application, really useful. So what's this called coin changing algorithm? Probably you'll notice that when you go to a supermarket, any supermarket, like a Giant or anything, or Whole Food, do you realize that when you buy something cheap, for example, 6 cents, whatever things, you give $1. Do you notice that the cashier, although probably most of them never train properly math, they can do this change very quickly, right? So very quickly, they can just give you quarter, several quarters, then dime or nickel. And they actually, everyone follow an algorithm which will make sure that the number of coins that return is a minimum. So that's interesting, right? The idea is turn out to be simple. Suppose, just give an example, you want to make a change of 56 cents. So what the cashier will do, give you 2 quarters to make a 50. Then give you 5 cents, right? Then make it a 55. Then give you a penny. So this is a greedy algorithm. So you use the maximum one, right? As long as it's less than whatever the change. Just keep on, be aggressive. And this will guarantee that the number of coins inside your pocket will be minimal. Do you get that one? Any question? But probably not many people think about the other way. Do you notice that, I don't know, probably you never live in the other country. Do you notice that most of the cases, your pocket is full of coins? Why is that? Anyone can guess? Do you have that kind of experience? Maybe it's because you're lazy and you always give someone $1, $2, but it gave you lots of coins return. Maybe it's a design problem, right? Design problem. Design problem means that whether this kind of denomination, like a 1 cent, 5 cents, 10 cents, 25 cents, is the best design. Anyone think about that? Right. So we will ask this question later. But you can see this is it's an interesting problem. Right? So this is one example. So the current currency denomination is 1, 5, 10, 25, 100. Actually, there's a 50 cents. But I don't know why it's no longer popular. Once in a while, you see this 50 cents. In reality, actually, there's a 50 cents one. Maybe someone later find out that this 50 cents is not that useful or something. Okay. So the key is that use a given currency denominations, devise a method to pay among the customer using fewest number of coins. And cashier algorithm, right? So at each iteration, add the coin of the largest value that does not take as past amount to be paid. Just keep on doing this one. So just instead of subtraction, you can do the addition, right? Just addition. So like you returned 56 cents, you just keep on adding. So you add 1 quarter, 25, another quarter, 50. Right? Then you add the nickel, then 55, then you add 1 penny, it's 56. Right? So cashier does not need to worry about whether I pay you with a minimum number of coins because it's guaranteed it's optimal. Okay. Any question on that? No question. Right. So this is another solution. This actually this is $1. $1. Yeah, in fact, there's a $1 coins in US, so it's not very popular. So make a $2, then this is 3/4. So it's a 2.75. Then you add the dime, right? And 85. Then you need to add the 4 penny to make it 2.89. So that's the algorithm. Okay, now let's see how you design this cashier algorithm. All you need to do is you just find out, you first put this denomination in the sequence. That's easy, right? 1 cent, 5 cents, 10 cents, 25 cents, 50 cents, 100 cents. Then the coin you selected, then if as long as the remaining is not the 0, that means you still need to pay your own. You select the largest K such that this value of a CK for the 25 cents is less or equal than whatever the changes, remaining one. But you need to find the largest one. If, yeah, then, oh, there's no solution in science, but in our case, it's always there is a solution. But that's another issue, right? Maybe in the test, I will test you. Is it possible that there's no solution? Think about it. If a country not carefully designed their denomination of a coin, you may not be able even to return the exact amount. The answer is simple, is that if you don't have a penny, then you may be in trouble, right? If you don't have a penny, then you cannot. So that's to say no solution found. But in US denomination, the currency system, there's no problem. Actually, in any system, you always add 1 cent there. If 1 cent is the minimum denomination, right? In worst case, you just return everything in 1 cent, but it's just too many penny, right? Okay, so once you select that, you subtract the CK from this total remaining one. So this is a new updated one. And this S is the coins, right? So whether you pick a nickel, dime, or quarter, you just put this thing in there. So you know that at the end, S give you the solution, what should be the best solution. So that's a natural way to ask, is the cashier, the algorithm optimal? Okay. So in turn, it's optimal. So how you prove this optimal? Well, this is another way to prove, which is quite nice. Again, this is the induction process. So the key thing is that you have denominations, right? So from 1, 5, 10, 25, 100, or this number can go on and on. the key is that you give an induction assumption. You say that the particular k, all the number before k are optimal already. So all you need to say that what happens if a number is between this denomination of ck but less than ck plus 1. All right, so in this example, for example, any number between 25 and 100, whatever you want to change, you start from there. So the idea is that in this case, we already know if anything larger than 25, I mean, suppose that you don't have a 50, you always use a pen, you're using the quarter, right? Quarter. Once you take this one from the quarter, and just continue to take until this number is less than 25. But once the number less than 25, what are you going to do? Then you can prove, say that based on the induction assumption, it's already proved. So that's the idea. So it's just like based on the intersection or whatever, the range, right? So the range is really between two adjacent denomination. Right? So you can prove that one. Okay. So the proof in this way, so we can claim that any optimal solution must also take a coin k. So that's a key, right? So if it's in range ck to ck plus 1, optimal solution have to take a k. Why is that? If not, then it needs enough coins of other type. So that means if you don't take if you don't use the k, then you have to use the coins with a smaller denomination. Is it correct? For example, in our case, just say that if you want to return 30 cents, I say that first you need to use a 25. If you don't use a 25, you have to use a smaller one, like a 1, 5, and 10. But in this case, you will use more coins. But they argue in a slightly different way. So it just say that the table below indicates there's no optimal solution that can do this. No optimal solution can do this. So optimal means, so they argue in a slightly different way. We'll see that. But then the problem reduced to, suppose this is true, then the problem reduced to coin changing x minus ck, right? Suppose you have to include ck. Now you include ck. Then you need to deal with kx minus ck. So which by induction is already optimally solved by Greedy's algorithm. So this is how you do it like a backward. Right? So you pick any range, you subtract ck, then the number becomes smaller. But based on the induction assumption, all the smaller one already prove optimal. Okay. So this is their argument. You have to pay attention to this one. So k in this case is 1, 2, 3, 4, 5. So these are the ck, means the denomination, right? Penny, nickel, dime, quarter, and $1. So this third column means all optimal solution must satisfy. Right? So you cannot use more than 4 penny. Why is that? Why you cannot use more than 4 penny? Because for optimal solution, you can never use more than 4 penny. Why is that? Because if you use 5 penny, you can replace by 1 nickel, right? So that's one. So that means the maximum value you can represent just by penny, only 4. You see that now? So that's why this 4 can never replace 5. Then for the next one, it's the same idea. For the nickel, you can never use more than 1 nickel. For any solution use 2 nickel or more, what happens? It's not optimal because 2 nickel can be replaced by 1 dime. Okay, so that means if only restrict to nickel and penny, the maximum number you can get is 4 plus 5 because 1 nickel, 4 dime, penny is 9. You cannot replace 10 by 9. So you can never really make a change for 10. Right? That's the idea. So this can just continue. Then they argue that you would never, any optimal solution can never have nickel plus dying into number of coins is more than 2. So that means you cannot have an optimal solution with 2, just say 2 nickel, 1 dying, or 2 dying, 1 nickel, or something like that. So the combination for this one is no more than 2. So this will be equivalent to like a 20, maximum 20 is a 24, which is less than 25. So this thing just goes on and on. Same argument for quarter, because 3/4, you add this together is 75, right? Because you cannot use a 4/4. Why? If you use a 4/4, $1 is equivalent to 4/4. It's better solution. But this one can only add up to 99, cannot replace 100. So all this kind of argument, this can continue. Right? Although in US currency, you don't have more coins. So this 100 is the maximum. So this is how you prove it. It's like a backward, right? And so it's kind of a very interesting way to prove why there's no other solution. Because there's basically no other solution unless that you use more coins. Okay. So this basically proves that. By the way, there are lots of thinking you can do. Suppose, so we briefly mentioned this, right? About what's the denomination is very good. And there's another issue is that if a country, if whatever king doesn't know anything about mathematics, you may come up with some kind of very weird denomination in such a way, although it's not a disaster, using the greedy solution may not generate the minimum number of coins. Have anyone think about that before? Right? Although it's not a disaster, but the greedy solution no longer exists, no longer optimal. Why is this possible? And the answer is a yes. Right? Suppose this is the structure, the US Postal. I don't know what's the situation now. I never follow US Postal stamp because it keep on changing, right? Keep on increasing. Suppose one particular year, this is an example, particular year, you go to a post office, there are different type of stamps. You have a 1 cent stamp, they have a 34 stamps, and then the 70 cents stamp. Suppose you want to buy a stamp, a total 140, right? So you go to the post office wait and say, okay, you have to pay 140. So you just buy. But now you cannot use a greedy algorithm anymore. Why is that? Because if you use a regular greedy algorithm, you come up a solution which is not optimal. Because you greedy, you first buy $1, they have 40 cents. The next choice is 34, right? Then you have like you're short by 6 cents. Then you have to buy 6 1-cent stamps. So many stamps. But the optimal solution in this case is 270. Okay. So that means the US postal system, this hypothetical. For this case, it's not about optimal if you use a greedy algorithm. Now the question, can you come up with a general method so that the greedy approach always optimal? Right? So this, you can think about this. So suppose I give this in the midterm test. Can you come up with some kind of method? Although the solution may be many. Yeah. But obviously you have to include one. Otherwise you cannot give an exact change. Okay, now let's look at the one problem is this one. I should go back to my previous problem. I mentioned this one. Why in US, lots of people pocket are full of coins? maybe you can look at this scenario. You observe all kinds of changes, right? So you can start with 1 to 9. So it means that if you have 1, you want to change 1, you have 1 penny. 2, you use a 2 penny, so it's 2 coins. 3 is a 3, 4, 4. 5 is okay now, you use nickel, just 1 coin, right? 6 is a 1, 1. 7 is 1, 1, 1. So it's 3 coins for 7. 8 use 4. 9 use this one. Actually, disaster happened is where you probably can imagine that. What happened if you have to change 99 cents? Use a 99 cents. In this case, you have to use 25, right? 3/4, 25. Then you add another 10 cents, then 85, another 10 cents is how many? Is 95. Then you still put 4 penny. So this is 4. So that's the 7. And imagine that all this one, the change is uniform distributed. Really means from 1 cent, 2 cents, 3 cents, 4 cents, all this change, uniform distributed. Can you design another currency system such that the average number of coins that you change is minimal? Okay. But the question is not complete. It depends on how many different denominations are allowed. Obviously, the more denomination, the better, right? For example, I can create a 1 cent, 2 cent, 3 cents, then a coin with 10 cents, coin for 20 cents, coin for, and so on, okay? But if you look carefully in the US system right now, so you have a 1 cent, 5 cents, 10 cents, 25 cents, and 50 cents, although it's not frequently used. And then you have $1, $20, $25, $10, $25, $20, $100. Actually, to me, it sounds very odd. Why it's not uniform? What do you mean not uniform? Do you notice that you have a quarter? You have a quarter here, right? But why there is no $25 bill instead of 20 bill? Right? No one really studied this one. Anyone maybe you can give me explanation, you can do some research. And yeah, so this is a very interesting scenario because I'm originally from China, so they use a slightly different denomination, but it's consistent. So under the $1, they have in fact, they have 1 cent and 2 cents, then 5 cents. And it's uniform. Really uniform means that 1 cent, 2 cents, 5 cents, then 10 cents, 20 cents, 50 cents, then 100, which is $1, then $2, then $5, right? You understand that? And all this thing. Now it'll be really interesting for you to study under the same number of denomination, which system is better? Better means that you want to minimize the average number of a coin that returns. Imagine all these ones are coins, right? Or coins. Can you design the better one? Or if I give you the limit, for example, I can give you a certain number of denomination. What's the best design so that the average number of coin returns the minimum, assuming the uniform distribution? Okay. In fact, when I teach this algorithm, I always use this example. Still, I cannot find the solution. Why US system come up with this kind of inconsistent denomination at different levels? Right? So why just, for example, quarter? But the dollar bill, there is no quarter. There are only $20, not $25. But it's interesting. So if you think deeper, there's lots of mathematical problem. I'm not saying this is bad, but it's just the current system. Right? Okay. So that's why at the end I mentioned about this so-called modular design. It's not discussed in the book. So modular means that a consistent changing rule for zero in the range, right? Within 10 cents, $1, $10, $100, and so on. Okay. So that's, but I heard that there's something interesting. I think in India, right? Recent year, the government tried to crack down the corruption, take out all the high notes, dollar bill, whatever. So I think this is a smart way. So then if you try to save some money, you store this, hide this money in a home, right? So they say you cannot really circulate this big one. Then where you hide those money? So $1, $10 is nothing. Yeah. So that's about the. So I think as we're almost done, I just want to mention this one final things. The greedy algorithm, there is a local decision. So you have to pay attention, local decision. So I mentioned about this wave algorithm, you propagate, right? Even for the activity schedule, interval schedule. So you start from left to right. So you have like a local decision. Looks like it's everything just local decision, right? You can just move from one direction to another. Even for the Dijkstra algorithm, you have a sequence. So you build a tree, you grow a little bit. But be careful, this one is still different than another set of algorithm, although it's not the scope of this class. It's called the local algorithm. In the greedy algorithm, you still use a local decision, but this decision result propagate from one side to another one. Propagate, it's a very important concept, propagate. Whenever you have a propagation, probably you cannot do a parallel. Parallel means that you cannot really cut the graph into multiple pieces in running Dijkstra algorithm. And you cannot really run this schedule for interval schedule, cutting the pieces to parallel, right? Because you have to propagate. But there's some algorithm, some application, it's called a local decision with no propagation. Then you can do it really local and very fast and parallel. So this is one of the algorithm I proposed, this is like 21 years ago. It's applying the social network. Just imagine you have lots of friends connected, and you have a Facebook or connection. Then one day, the government said that you need to shut down. But condition that you shut down your site, you cannot disconnect other people. Right? But the graph structure, I mean, you have to be careful that when you disconnect, you remove, and you may disconnect the whole network. So can you do that local decision, but you have a global property, global connectivity? It turns out there's one algorithm. I mean, very simple. It's really that, suppose I have 100 friends. Or I need to check where pairwise my friends are connected, directly connected or connected through other nodes with high priority. Then if any pair of my friends can directly connect, I can go to sleep. And all this decision can be parallel, done at the same time, one shot. Right? So if you're interested in those kind of things, so later you can read some literature about this local algorithm. Unfortunately, many problems cannot be solved using local algorithm without propagation. Okay, I think the time is up. Let's stop right now. Don't forget to submit your homework. I give you the Canvas link, so you know how to submit. Do you have any question? If no question, let's stop here. Thank you. I will see you next week.
Thank you, Professor.
Thank
Goodbye.
you.
Thank you, Professor.
Professor.